Hello, so I'm Honza Klusáček, and I will be talking about puzzle hunts and puzzles, and I hope that I have some tips for you about how to approach a hard problem that you might want to solve. So first question, does anybody here know about puzzle hunts, or have you heard about TMOU or something like that? Okay, so some people do, some people don't. Okay, so what is a puzzle hunt? Well, it's basically a competition in problem solving for nerds. So you need a team, and you need a place to start. And then you go to that place of start, and you find a puzzle there on that place. And that's the puzzle, and then you try to solve the puzzle. The puzzle can be actually anything. So you brainstorm some ideas and try different things. And eventually, you find the correct idea, and you get a solution. Now, sometimes you can get some hints in some games, in some puzzle hunts, but not always. And then, once you have the solution, you go to the next place, and then you find another puzzle, and then you repeat until you reach the end, or until the time is over. So this is a puzzle hunt. And what is a puzzle? Well, puzzle can be almost anything, some kind of problem. So I have an example of puzzle for you. So yeah, some more pictures. So this is a picture from last year's TMOU. We were on the Spielberg Castle. We had a puzzle in a cave, which was very nice in the middle of the night. We had a puzzle in the city park in Brno, and you can see it's filled with people. More than 1,000 people participate in TMOU every year. So that's the biggest puzzle hunt in Czech Republic. And last year we installed also this wonderful gleaming cube in an old monastery. So now to the puzzle example. This is what a puzzle can look like. So yeah, take a look at it. You can see there are some letters and numbers and other stuff. So where to start to solve it? I suggest that we have to start somewhere. So why not with numbers? We like numbers. So here's 3, and here's 9, and here's 19, and here's 26. And in puzzle hunts, we like 26 because there is 26 letters in the alphabet. So 26 is this magical constant that you just want to get. So these are all the numbers. And because there is no number bigger than 26, we can translate them into the alphabet and get this message, which says basically that we can ignore the numbers. Well, okay, that happens. At least we now know that we don't care about the numbers. So where to go next? What should we try next? Letters. Yes, let's try some letters. So here's all the letters. And after a while, you would find out that there are exactly 26 letters. Ooh, 26, we like that. And that every letter is there exactly once. So we can connect the letter into an alphabet. So we have A and B and C and D and so on and so on. And here's Z. So that's nice. We like that. And what haven't we used so far? So what can we do now? We have this alphabet, we have this line. So we still didn't use any of the other symbols in there. So you can notice that there is like, on each segment of the alphabet, there is a symbol. So there's star, here's dash, dash, star, slash, and so on and so on. And if you write them down, it's Morse code. So now we translate the Morse code, and we have the solution. And voila, you solved your first puzzle. Isn't that nice? Okay, so this puzzle was fairly easy. Let's get to something more difficult. So last year, I was organizing TMOU. And this is a puzzle that I made, and this is a puzzle that was most difficult to make. And I will talk about the problems that I encountered while making this puzzle, and some tips about how I solved it. So first, some description. What was the puzzle about? So I suppose you know this game. This is a board. Some dots are connected into a path, and you have some figures. And you have dice, and you roll the dice, and you move the figures. And overall, it's a quite boring game. So how to make it less boring? Basically, get rid of the board altogether and start with the dice. So this is the dice. And the main idea was to put the board onto the dice, because there are some dots as well. So we can connect the dots, and now we have the path and that the figures can follow. So we put a figure on there. And because the figure is sticky, it doesn't fall down. And because the figure is heavy, when you roll the dice, it will land on the face with the figure. Ta-da! Number 4. So now we can move the figure by 4. So it's 1, 2, 3, 4. And then you can repeat and again and again. And because we need to get some solution from it, as from every puzzle, I put some letters onto it. So you write the letter that you step on. And because this is TMOU, the hardest puzzle hunt of them all, I just added 2 more figures. So it's not that easy anymore. So is it clear so far? So we have this dice. You change the center of mass by putting a figure there. And then you roll it. And then some numbers. Then you get some number. And then you move 1 figure. And then you repeat and roll again. So this is the idea of the puzzle. And I was quite happy about this idea. And spoiler alert, this is the final product. So you can see the 6 faces of the dice. You can see like this is the face with 1 dot and 6 dot, because we still have this dots on playing dice. You can see this. There are some letters. And so we have to put some letters in there. You have some path connecting the dots. So you have to figure out how to connect the dots. You have to figure out where to put the starting figures. So this is the starting point for first figure and so on. So yeah, where to put them. And also you have to decide on the direction. So yeah, kind of a lot of stuff to decide. And the question was, is it actually possible to make this work? So some estimates. So there is roughly 3.8 times 10 to the power of 22 options, which is kind of a lot. Definitely too many for a human. Also too many options for a computer, but more that later. Also, there are some other facts that you might notice, that what happens if you have 2 figures at the same dot? Like, will 1 figure get out, or what will happen? We don't know. Is it always clear what number will I get when I roll the dice? Yeah, maybe, maybe not. Maybe it's ambiguous. And what are the implications of that I have 3 figures? So only 1 moves at a time and 2 stays. So there are some constraints here. And also, I want to connect all the dots into a single path, a single circle. So all these constraints are kind of like tangled together, and it's too tangled for a computer to solve. Just formalize it and put it into solver and run it, and you get a solution. It's not possible to do. So to summarize, we have a computer which is able to do some brute force calculations and which has some structures, and we have a human that have some insight and imagination. And I suggest that you have to use both, and that the Python is a good interface between these 2 entities. It also looks like a small plus. And if you combine human power and computer power, you can do almost whatever. So here comes the lesson on how to solve difficult problems. Lesson number 1, try to simplify. So forget about the dice. This is the path that I have. And what I said was, okay, 2 figures will not step at the same dot, not at the same time, not ever, meaning that these are the dots that only 1 figure will step on. And these are the moves that the figure will do. So to move this figure, we have to roll 5 here, move it by 5, and then 3, and so on and so on. Also, other figures will have their own dots. So this is 2nd figure and 3rd figure. And then you have to put the starting point somewhere. And based on this simplification, I get this sequence of numbers that I want to roll. So first, I want to roll 5 to move this figure here. Then I want to roll 1 to move this figure, and so on and so on. And then I transform the problem into checking whether this kind of sequence is even possible to make or not. The interesting thing is that by introducing a new constraint, I actually simplify the problem, because this constraint is easy to check, and it transforms the problem into something else, and it leaves some stuff out that I can do last. So for example, I don't care about the letters anymore, because that's something that I can decide after the whole cube is constructed. So, and also you can use iter tools, combinations, which is really useful if you want to try some combinations and combinatoric computations. Lesson number 2, pre-compute. So I had this function that for 3 positions computed what numbers will I get. So if I get these 3 figures, I will roll number 3 because the center of mass is closest to number 3. So I did some magic, and so I suggest that you use some kind of dictionary and you pre-compute all the possible options beforehand. So then if you have this kind of expensive computation, some expensive function, you don't have to call it all over again because you have it in dictionary. And dictionary lookup is really fast. Also, if you are tech-savvy, you can use this decorator, which does basically the same thing. Yeah, look it up in functools and itertools product and so on. And also, I pre-computed a whole lot more. So also some sequences of moves. I don't know how to use the laser pointer. Sequences of moves and so on. So if you have some difficult calculation to make, I suggest that you compute it beforehand and then just load the results from somewhere. And also, yeah, both ways, because that's nice. Lesson number 3, this is the most important in my opinion, to try to think in Python. Because Python data structures are well designed and incredibly powerful. So I'm talking about tuples and lists and dictionaries, and by extension, name tuples and decs and default decs, which might be useful in some cases. And if you use them while thinking, it will help a lot because you save yourself a lot of hassle while implementing it. And also, if you use the notation on the paper, and then you see the same notation on the screen, you know that this is the same thing. So don't think about line connecting dots, think about a list of dots, and don't think about 3 figures at some place, think about 3 tuple, and it will make your life much easier. So for example, this was a tuple for me, so I have first figure, second figure, and third figure on some dots, so that's a 3 tuple, combined with the integer, which is the desired output of the next row. I put it into a dictionary, which was this pre-computed function, and I got the list of all the possible dots that I can step on, so that I get number 2. So this is the initial configuration, and if I move this figure to either of these spots, I will get number 2. This is what it says. And I use this function/dictionary lookup in a recursive iteration, and I was searching this number of options to find it. And final lesson, extra lesson about large numbers. So rule of thumb, if you have less than 1 billion numbers, billion options to check, it's fairly easy. You can just go through them all. And if you have more than 1 trillion, it might be not possible because computers are not that fast. So if you remember from before, my number of options was way, way up in the right, 9 to the power of 22. And at this point, the speed of Python or the slowness of Python doesn't really matter, because if you increase the speed 10 times, you move by this tiny bit on a logarithmic scale. And what matters in these kind of problems is developer speed. And this is something that Python really helps with. So yeah, I spent a couple of days on this problem, actually, even with Python. Next short lesson, I will encourage you to find interesting properties of the problem. So just explore and think about some consequences. For example, I found out that if I want to roll 6, and then 1, and then 6 again, it's just not possible because of the 2 figures staying in place. So whenever I see this, I just say, OK, next sequence. and you can take advantage to them and prune early. And the last and most hopeful lesson is that large number of options may not be a disaster. So even if you have large number of options to check, if you are not looking for the one best, only one solution among all of them, it might happen that the number of correct options rise as well. So I think, I don't know it for sure, that there were many solutions for my problem. And this is the approach that actually helped me to reduce this kind of problem that I just said, okay, I will check at random just some sequences, and every 1% of the sequences that I checked were correct. And so keep faith. And that's all from me. I guess we will maybe have some questions, or I can go back if you haven't understood something. I think I was talking pretty fast. And if you find puzzle hunts at least mildly interesting, I would like to invite you to this puzzle hunt Interlos, which is next month. And there are some programming and logical puzzles in there, so I think that you will like it. So check this out and ask questions.
Thank you very much for an interesting talk. We have only one question. Where do you get ideas or inspiration for creating puzzles?
Okay, so basically everywhere. And it's kind of like if you go to puzzle hunts and see a lot of them, then you start looking for places where you wouldn't suspect before. Like I go to a shopping mall and there's like interesting tile pattern on the floor, and it's like, oh, this would be an interesting puzzle. And also, if you're solving some other puzzles, you might get into some dead ends. So you are solving, okay, maybe it works like this, and then you find out it doesn't. But maybe this idea that you have is a good idea for a puzzle of yours to make. So that's the most frequent source, I would say. So yeah, you have to solve other puzzles to think about yours.
Thank you very much. Applause for Honza.